In our last video, we talked about the meaning of some of these words, parameter, and the separate parts para and meter. All right. We had looked at what is meant by a family of curves. So that what we call curves in mathematics would also be a straight line. All right. And we looked at the meaning of the word envelope as used here. All right. Now, what we're going to concentrate on is finding the envelope. All right. Going to see what that is all about. Now, in doing so, I made a few notes here. As we go along, you will see that there are some envelopes that are what are called non-traditional envelope. Right? The definition of the envelope, as we saw before, is a certain curve that is tangential. In other words, touches each member of the family of curves. But we see in some cases that what we derive, what we get as an envelope actually cuts each member of the family of curves instead of touching them. And if you look that up, you look up the information to explain, give an explanation as to what happened in that case, right? You will find information such as that the classical definition of an envelope would apply when there's a smooth tangency condition. But in these cases, where it seems to cut them, due to the algebraic nature, such a condition leads to no meaningful envelope. And what you will be observing is not an envelope in the strict sense, but rather a critical locus related to the discriminant of the family of curve. So in non-classical cases, well, for example, in some quadratic curve, you have the discriminant, which is b squared minus 4ac. That tells the various types of quadratic curves. All right. So in non-classical cases, the envelopes can appear to intersect or cut through the family of curves, especially when the family of curves is algebraically degenerate. Right? There might have them crossing one particular point, all of them cutting each other. So the envelope would cut through them instead of being tangential. Alright? Now here we also see that not all families of curve have boundaries. I wrote boundaries, but I could say have an envelope, right? Now, what are the steps that you should take in finding the envelope? Let us see. Step 1. Step 1. What should you do? Well, write the function of x, y, and that is, write the function of the variables and the parameter equals 0. Right? So just to show what's going on, an example, suppose you have y is equal to mx plus 3. Now, what you do is make the variables, the parameter, and any constant all together on one side. Then you say equal and 0 alone on the other side. So you could say this becomes mx plus 3 minus y equals 0. Alright? So that's step 1. What about step 2? What is step 2? In this case, you differentiate partially with respect to the parameter, right? So you find the partial derivative of the function with respect to the parameter. Let me draw a line here to separate what's going on. So here you're going to find delta of the function by delta of m. Generally, partial derivative of the function with respect to the parameter, right? I use p to represent the parameter here. So in this case, what we have on the left hand side, you differentiate. What we're going to get is x, right? Because x is a constant, y is a constant for now, at least, and 3 is always a constant. So in this case, m is equal to, when you differentiate 0, we get 0. So x equals 0. Alright? So that's what we get. And then, as outlined up here, solve given the derivative. Solve the given and the derivative simultaneously. Alright, let me just type and add solve the given and derived, D-E-R-I-V-E-D, solve the given and the derived function. Alright, so that's a neater way of putting it. Solve the given, comma, and the derived functions simultaneously. Alright? So, step 3. Solve the given function and the derived function. Of course, the derived function is the derivative of the given function, right? Simultaneously. And of course, what will happen? This will make the parameter disappear. Right? This will make the parameter disappear. Alright, so in this case now, we use substitution. Use the substitution method. So since we know that x is 0, y is equal to m times 0 plus 3. So y is equal to 3. So in this case, y equals 3 would be our envelope. Alright. Let's look at some of these functions. Y equals mx plus 3. We're going to give m various values. Y equals mx plus 3. So I have the GeoGebra graph plotter here. Right. Now let me put in y equals x plus 3. Right, so that is our curve, y equals x plus 3. Let me make it thicker. Let me also put in y equals 2x plus 3. So we have another one there, y equals 2x plus 3. Let me thicken it too. Then we have y equals 3x plus 3. Okay, so we have yet another one. Let me make it thick. Suppose we put y equals negative x plus 3. Right, we plot this graph, y equals negative x plus 3. Make it thick. Let's put another one, y equals negative 2x plus 3. Right, we have yet another graph there. Right, want various colors for them. Then we have one more, y equals negative 3x plus 3. So we have this one here. So we have various lines, various straight lines referred to as curve. Now, what was the thing there? The envelope. The envelope was y equals 3. So let's put in the envelope. Y equals 3. This is the envelope of the family of curves. But as we said before, it's not a traditional envelope. It cuts these. Alright? It actually cut through the curve. Now, we're going to look at other situations where we have this envelope that does not follow, does not obey the classical definition of envelope. But after that, we're going to look at some that do. But just before we finish this video, let's look at another example. Just modify the, suppose we have y equals a specific number x plus our parameter. Y is equal to x plus c. Now remember our thing there, our step 2, differentiate. Oh, step 1. We don't want to skip over step 1. X plus c minus y is equal to 0. Write it like that. Then differentiate with respect to the parameter. Our parameter is c. So when we find the derivative of the function with respect to c, this is 1c. So remember, like when we have y is equal to x plus 2 and we find dy by dx, x is raised to the power of 1 times x to the power of 0. So 1 times x to the 0, which is 1 by 1, which is 1. You have to remember that. So when we find the derivative of c, we're saying that c is raised to the power of 1. So it's 1 times c to the 0 now. So what we have is 1. Right? Now here, even when we differentiate the right hand side, we get 0. But we're saying 1 equals 0. So this seems to be some type of contradiction, because 1 cannot be 0 and 0 cannot be equal to 1. What I can tell you is that the envelope does not exist. This function does not have an envelope. Alright? Let's look at the graph and see. If we let's just change these now. We have x plus 1. Alright? And let's change this to x plus 2. Remember, we're saying that we have x plus c, so we're changing the c. Then this to x plus 3. So this is x plus 3. Then let's change this to x plus 4. Alright. So in this case, y is equal to x plus, say, 5. In this case, y is equal to x plus 6. Alright. Now, we no longer have our y equal 3. Here, all these lines are parallel, they point in the same direction. There is no line that touches all of them. So it does not have the equation y is equal to x plus c, parameter, does not have an envelope. Alright, so in another video, we'll continue and look at other examples.